Um, hey guys, I just got out of LeetCode weekly contest. This was the contest. What was the naming of the contest? This was the contest 388, and I just got out of it. Thankfully, I actually managed to solve all 4 problems here, and I just want to spend a little bit of time talking about problem 4. Because apparently in the discussion thread, a lot of people seems to actually struggle with problem 4 here. And I think problem 4 is actually a very interesting problem. It's a dynamic programming problem, but there's a lot of nuance to be considered for that one. And I think it would make for a really good video to do a deep dive explanation on it. So the problem is called maximum strength of k disjoint subarrays. So let's just read through this. We are given a 0 index array of numbers, right? And they could be positive or negative. The strength of x subarrays is defined as sum of 1 times x minus sums of 2 times x minus 1 plus sums of 3 times x minus 2 minus sums of 4 times x minus 3 and so on, where sum I is the sum of elements in the ith subarray, and formally strength is this equations. This is really confusing, but I think walking through an example will actually help us a little bit here. In terms of dividing a subarray. So let's just finish this and we'll go to an example. We need to select k disjoint subarrays from nums, such as the strength is maximum, and once again strength is here, and we want to try to divide into k disjoint subarrays that have the highest strength. We have to return the maximum possible strength. So we simply return the strength. We don't actually need to return how we perform the divisions. Okay, so let's actually go through an example to understand how are we calculating the strength here, which is very complicated. So for example here, right, this is the array, and we have to divide into 3 disjoint subarrays. So a disjoint subarrays just means that you have subarrays that don't overlap with each other. So for example, this is like a number line. You have to select something like this, right? You cannot do this because they would be sort of overlapping with each other here, and this exercise does not allow us to do that. And then for each of these strength, we actually have a score for it. So assuming that we divide into k subarrays, here in this case is 3, right? So k equals 3 here. The way we calculate the score is that you can see that there's an x here. X actually goes from k to 1, and x is decreasing over time. So you attach like an overall multiplier of x here. So 3, 2, and 1, right? You also have a sum of each subarray, right? So you have the sum of the first one, you multiply that with this multiplier, as you can see here. So here you multiply by this sum, you multiply by this sum, and you multiply by this sum. And notice here that there's actually a plus and minus that is alternating sign as well. So whenever that your multiplier is odd, then you will do a plus sign, and when it is even, then you do a minus sign, and when it's odd, you do a plus sign. Why do I say so? Because notice here that they actually force k to be odd. So it is always the case that your first number will be an odd number. So you alternate odd, even, and odd, and you kind of have this kind of calculations. As an example of how we calculate the score, right? So here is 1, 2, 3. This is the example provided by the exercise here. The way they say that is the best possible way to do this would be this subarray and then this subarray, and then this subarray. So here we have the sum of 6 that is multiplied by 3. This is sum of -1 that is multiplied by 2. And this is sum of 2 that is multiplied by 1. Right, so let's do the calculation. So 3 times 6 is 18. This is -2, and this is 2. Now, because of the alternative sign, you have plus 18 minus 2, so now it's actually a plus, and then plus 2. And then we have 22, which is this 22 right here. One thing to note is that you actually don't have to cover the entire arrays here. There's a note here, right? Note that the selected subarrays don't need to cover the entire array, which means that you actually don't need to select every single numbers here. You can just simply select when it's advantageous for you, right? And as an example, here you have to select one subarray. If you select like all 3 of them, right, then that would be like a -6 score. But you don't have to do that, right? You just need to select -1 here. You have to select a subarray, which is important to note. So you cannot have a subarray of nothing. The subarray has to be at least of length 1, which I think it is actually kind of noted somewhere here. I don't think it is mentioned, but you can understand that the subarray has to be of length 1 at least, which will be really important later on. So once again, you can see here it is a multiplier 1 times 1 times -1, so the output is -1. Okay, so our goal here is to return the highest possible number that we can achieve, the highest kind of strength, the highest kind of division in which we can have the highest possible strength for our disjoint subarrays, right? So how do we tackle this problem? First of all, I think it's actually very helpful to think about this in terms of a dynamic programming problem, right? You can see here that because we have like an n and because we have like a k, we can sort of try to formulate our problems into a smaller problem, right? So let's say you have like an array that have this length. What is our subproblems? Let's think of what is our subproblems here. We have to select the highest strength, of a disjoint subarrays that is up to character n, right? So let's just put an n here, and then we have to select k of them, right? So what if for this character n, right, we have a lot of choices in terms of this. I think one very helpful way to think about dynamic programming here is whether to pick it or not pick it, right? So here, there's a lot of way we can pick this subarray n, right? We can pick from here, we can pick from here, we can pick from here, we can pick from here. So essentially what we do is that we can pick this subarrays, calculate the sum, and then we add this sum with a DP of up to this point, which let's just call this I, right? We can have a DP of up to point I minus 1 and then k minus 1, right? And I think this is actually a fairly straightforward way to go. So this dynamic programming problem, we can have like a storage of n times k, which is 10⁻⁶. And then we also have 10 - 6, and then we have like this sum. So I think this is actually a pretty straightforward. Now we can make this sum more efficient by having like a sum so far tricks. So you can calculate the sum up to n and then sum up to I, right? You just calculate it one time, and then you take the first sum minus the second sum, and then you have this array. So there's a lot of ways to sort of efficiently calculate this sum without us having to sort of iterate through each array every single time we consider I. Or the other way that you can go about it is that like you can go I backward, right? You can go I backward and then just keep adding this number on to the sum, right? Now make sure that you have the correct multiplier for this sum. So this stuff, this is the part of the exercise that the contest programmer, they're trying to make it really confusing because we have to add and take care of a lot of stuff. But it's actually quite simple in that you simply need to multiply with total. So there's like a big K. Let's call this like a really big K, right? This is the K total minus K plus 1. Because we select the array from right to left, notice that this goes like 1, 2, 3 upward, right? It starts from 1. So if you have K left, which means that you need to, that you need a multiplier of 1. So it's K total minus K plus 1 here. Times what? As I mentioned before, the multiplier here is minus 1 if it's even, if K is even, and it is plus 1 when K is odd. So what you have to do is that you have to do -1 to the K plus 1. Very confusing, but you just need to kind of have this part correctly. And then you have like a DP here, and I think we're all good. Now, if you do this solutions, it's not gonna work. In fact, this is actually the first solution that I ever did for the contest, and I actually got a little bit of a timeout in my results here. Let me go sort of go back to that. And there's a very specific reason. There's a very specific reason for this timeout. Oh, okay, I think I can check my submissions here. Time limit exceeded. You can see here, this is my solution. Interesting. I don't think they actually load the. I don't think they actually load the previous solution. Oh, okay, right here. So here, right? You can see here. This is the way that I set up the dynamic programming solutions. I have a memo of K times n times K, right? Where memo nk will represent the maximum strength of K disjoint subarrays up to this character, right? And I consider all the choices for the current subarray. So I go backward. You can go forward or backward. I think in this case I simply go forward because I already have the sum so far. And then I simply just consider whatever the choices of subarray that has the highest score, and then I store it in a memo. Now the problem with this solution is that yes, our storage is n times K, which is 10 to the 6. We actually have a for loop here. And this for loop actually loop all the way to n. So in the worst case scenario, we actually loop n times for each recursive call. So the actual time complexity of this algorithm is ode of n times ode of n times k, where n times k is the total possibility of the DP input, and n is the time complexity of each call. And unfortunately, if you multiply these together, as we can see right here, n can go up to 10 to the 4th, and n times k is 10 to the 6th. So total together, they are 10 to the 10th, which usually means that it is a timeout. Every time you go over 10 to the 9th, right, you need like more than a billion operations, and each operation is 1 a nanosecond. So now you already get like more than 1 second. So usually when you multiply that and it reach 10 to the 9th, you can usually assume that your algorithm will time out here. Okay, so that is indeed the problem, right? The problem here is that we are having a loop inside the recursive call. I think this will trip up a lot of people here. Having a loop inside a recursive call causing a time limit exceeded. So the issue is that like we actually need to frame this problem even further smaller, so that we have less choice inside the for loop. Less choice inside the DP call. And the way to do that is that we have to reduce the amount of choices that we do. So how can we reframe this problem so that we have less choices? Right now we are choosing the entire subarray, right? What if we only focusing on considering the very last element of it? If we consider the very last element of it, then what choice do we have, right? We can either pick it or we don't pick it. Now, if we pick it, right, then we simply add the last element to the score. So let me go through a different array here. So now let us reconsider, and let us call this the last element, right? Which let's just call it j here. Now, what are some of the choices that we have here? So choice 1, we pick j, right? If we pick j, then what we can do is that we can add the score of j, which is a very specific score. So it is nums j. Actually, let me use a different color here for like the, so nums of j times kt minus k plus 1 times -1 to the k plus 1. All this good stuff here. Now, that is not the only thing that we have to make a decision here. We can pick j, but keep the subarray going, meaning that we keep picking further, right? So pick j and keep picking. We can have also choice 2 as well, meaning that we pick j, but then we stop picking, meaning that we kind of stop our subarray here, and everything else that is coming is a new subarray. And there is an implication for this. Because these choices are actually different in score. They have the same part in the score that is picked up from getting j, but the DP part is different. So when we pick j and keep going and keep picking, our DP will be let me do this. Let me just kind of pull it right over here. Our DP will be what? J minus 1. So we kind of like get all of this character. K, because we are still picking for k, right? We're still picking for subarray k here, so we're not changing k. But for choice 2, pick j and stop. Our DP become j minus 1, k minus 1, And this k minus 1 is very crucial here, because this k minus 1, when it goes into this, the way we construct the first score from picking will be very different. So despite being pick versus not pick is actually very, very decisive here. So what about some of the other choices that we have? We can also have choice 3, which is stop picking, meaning that we don't pick j anymore, right? So if we don't pick j anymore, our score will be 0. But then the interesting thing about choice 3 is that depending on whether we are picking from the previous subarrays or not, the DP cost is different. So if we are picking from the previous subarray and then we stop picking, then it's fairly straightforward. We have a DP j minus 1 and then also k minus 1. However, if we stop picking, but then we are not actually picking for the previous subarray either, meaning that this is actually the first element, then we actually do not have the luxury of having a k minus 1 here, because we never fulfill our obligation to actually pick a kth array. So now you have a DP of j minus 1 of k. And you can see one of the problem with this kind of setup, right, is that right now we don't even have any method to really differentiate between these two call here. Let me just kind of move around a little bit here, just to be a little more clear. Okay, you can see here when we stop picking, there is nothing like, it's actually very important for us to know whether we are picking or not, otherwise we cannot differentiate these two, right? So the trick for this DP is that now you need another argument that is added to the memo, called whether you are part of a subarray or not, or whether you're picking or not. So we need to add a picking here and picking here. So for the options of pick j and keep picking, if we keep picking, then this should have a true here. If we stop, then this should have a false here. Now if we stop picking, then it should always edit another false as the third argument right here. And what this does is that depending on true or false, depending on whether we are picking or not, we will treat the third case differently and have a different recursive call for the third case. So now once we have choice 1, choice 2, choice 3, which means that for every recursive call, we only call 3 other calls, right? So that actually helps with the time complexity by a little bit, or actually by a lot, because now we don't have this O of n anymore. You only have this as an O of 3 now. And if you have O of 3 times O of n times k, then that is just 10 to the 6th, right? And usually when your algorithm sums up to 10 to the 6th, it is a sign that your solution will be accepted by LeetCode. So yeah, that is the directions that we need to take for our solutions. We actually need a 3-dimensional memo. It has to store essentially the memo positions represent what is the maximum strength if you pick up to character n when you have k subarray left, and when you are picking for some subarray or not. So that is the way that we are gonna construct our code. So let's actually come to the coding solutions. So this was the solution that I ran and I got accepted here. And first of all, as I mentioned, I set up a memo. Notice that this is the n times k memo. But here I also have a range of 2, which represent true and false, right? True and false also match up very nicely to index 0 and 1, so you can actually also do this here. One tips that I would give for everyone here is that for the true and false dimensions, you should actually put it to the last, because when you sort of try to debug, right, if you only want to debug a certain part of the memo, like only the true part, you can do for row in memo true, for example, and then you print the row. So as you can see here, when I access the memo, the fact of whether we are picking or whether we are part of a subarray is actually first in line here, and that makes the print and the debugging a lot easier. So once I set up the memo, the sum so far part is actually no longer relevant anymore. So this is a little bit of a redundant code I have not removed from my previously wrong solutions, but here we can make a recursive call, right? In the recursive call, we have j, we have k, we have whether we are picking. We need the raw k. This is the k total that I mentioned from the previous slide, and then we need the memo, right? Whenever I construct a recursive call, usually I always have a lookup case. The lookup case is to check whether the element is already in the memo or not, and then if it's not none, then I return it, right? So quite simple. I have a base case, so if we have nothing else to pick, we have no more arrays to obligate ourselves, then we just return 0 immediately. You can or cannot store things in the memo here. It doesn't really matter, but I usually like to just store it just for, I don't know, consistency. In some other problems, you might have a boundary check case that you should probably put even before the lookup case, because the boundary would actually violate like the memory location. So you probably should have a boundary check before the lookup case. It's very popular for the kind of, I don't know, counting island problems would be one that I think a boundary check case would be helpful here. But here you just need a lookup case and a base case. Now you need a recursive case. The way I structure it is that I have a multiplier. So this is mult. This is exactly the check for whether k is even or not. So if k is even, is -1. If it's not, then it's 1, right? And here are my 3 choices. First one is pick and stop, which have this score. Pick and keep going, which has this score. And then not choosing, which are these score. Now, notice here that I don't calculate all the score first and then pick the max score. And the reason for that is that not all the choices is available. I like to do max score, and then I do this kind of max score, and then the score that is being considered. And the reason that I do that is that, for example, the select and go, right? If we select and keep going, which means that we don't reduce k, but this choice is not always possible. And the reason for that is that you need to have enough numbers to ensure that the remaining numbers can still make for k subarrays, right? Do you remember that I mentioned that each subarray needs to have at least 1? This is where it plays here. Every subarray has to have at least 1, so we need to make sure that if we do this, then there are still enough number to pick. Same thing for the choice of not picking. If you are not picking, right, and then you decide to not pick, you reduce j by 1. So there is the same condition here, because you also have to make sure that because k doesn't reduce, the remaining numbers are enough. You have at least k numbers left to actually pick for k subarrays here. Now, if the choice is legal, notice here that we don't have this part anymore because we don't pick, and so we don't add any point. And then this is the max score. Now, same thing for if picking. Notice that we don't need the conditions anymore, because if both j and k is pushed by 1, then we are guaranteed that whatever, like if j is already bigger or equal to k, then j minus 1 will be bigger or equal to minus 1. So we actually don't need the check right here, as you can see. And then same thing, max score. We store the max score, and then we return the max score. So yeah, that's about it. Once you do the recursive setup, then yeah, that's already the entirety of the algorithm. You simply just need to return the location in the memo that represents your problem, which is that, like, hey, what is the maximum strength of k subarrays picked up to character n-1 when you are not picking anything yet, right? You can simply return this recursive call, but usually I like to construct it this way so that later on I can try to print the memo if I want to. Okay, so I think that's it. I think this is a very interesting problem. It really teaches us that there are actually multiple different ways to set up a dynamic programming problem, and that just because you found a solution to a DP problem doesn't mean that it's going to run in time. You really need to dig deeper, and also, as I mentioned, take care of the number of calls within the recursive call as well, right? Because they also affect the time complexity as well. Yeah, hopefully this video was helpful. Good luck, and I would encourage you to try this DP for both. Try both approach. Try the dynamic programming for both approach. I think this is a great learning opportunity, and I think it will certainly help you to future DP problem. Yeah, thanks for listening. Cheers and good luck.